Thank you. It's always a pleasure to speak here, and especially in the basic notion seminar, because I've spoken so often here. And it gives me an opportunity of describing some rather elementary things. The objective of the lecture is to prove the following theorem, which will not contain complete definitions. It will come later. If rho is a linear representation of finite dimension in characteristic 0 of a finite group G, and if it is an orthogonal representation, that is, it fixes a non-degenerate and fixes a non-degenerate quadratic form, so that really it is a map from G into some orthogonal group of V. So if you have that, and if P is a prime, not 2, then the reduction mod P of rho, now we have to see what it means, is also an orthogonal representation. For a quadratic form, which I will describe. You see, that kind of thing is, when you see it, I just needed it for something I was doing. And I could not find it in the literature, so I proved it. But it is rather simple. It is elementary, and the full lecture will be to explain why it is elementary, which is not completely obvious. Well, the first thing you have to do is to give a meaning to the various words. I guess the words up to there are okay. I think that's okay. But then the reduction mod P is not quite okay. And that involves speaking of discrete valuation rings. Discrete valuation rings. I suppose that most of you are familiar with it, but let me just say that such a ring, I will denote by R. It will have a field of fraction K. It will have only one maximal ideal. Which is non-zero. And that ideal will be a principal ideal, so I will denote by pi a generator of, well, M generator. Right? And then, of course, the residue field is a field, and then I will denote it by little k. I guess I've not forgotten much. Did I say that R is a principal domain? Maybe I should say that. R is a principal domain. But with just one non-zero prime ideal, the M. Now, you encounter those things typically when you do number theory and you want to go from characteristic 0 to characteristic P. Most of the methods consist in saying you have some data over K, and you are given this R. Then you try to reduce the data, if you can, to little k, and then you try to get properties from capital K to little k. The typical case that number theorists use that is when K is a p-adic field, of course. K is Fp. R is a p-adic integer. But it's also interesting to do that in equal characteristic, because that would mean, for instance, you have something which is happening on some variety, and then you want to see what is happening on a hypersurface. And then you have also a ring. But that would be the most interesting thing. Okay. Now how does that work? Oh my God. That is not the question of the button, that I won't have anything to write on. No, it's that one. Okay, you keep that in your mind, and that's all. But there is almost no. Oh. This is ridiculous. You all remember the statement of the theorem, and if you don't, it will make it easier for me. So, okay, so now we can start describing things. We will have a G, let's say a finite group to start with. Later on, it will not be finite. And a linear representation. That means we have a vector space V over K. And we assume that G acts on V. Now, we need the notion of a lattice. R lattice in V. And that's also something very standard. Lattice L is an R submodule. One way to say it is that it is free over R of rank the dimension of V. But of course, that also means that K tensor RL is V. And when we have a lattice, the interest of having it is that then we can divide it. L over pi L now is a vector space over little k. Is a k vector space. Suppose we note it Vk. Well, of course, it depends on lattice L, but one should put some L somewhere. Now, suppose we have that situation. Now, it's not difficult to see, it's pretty trivial, that there is a lattice stable. So there exists a lattice L, which is G stable. A proof, you take any lattice and you take the sum of its transforms by G, and it is a lattice. So really, nothing for that. Notice that this will be the only place where I use that G is a finite group. So for what I'm doing, the good hypothesis is that G is a group which acts on V and stabilizes at least one lattice. There is an even simpler way of saying that. You could say that, well, the image of G, this in, well, in GLV, but it is in end V. And in a vector space over K, you have the notion of a bounded subset. A bounded subset is something which can be put in a lattice. And if you put a metric, it will be the usual. So my hypothesis here is that the image of G is bounded. But the group could be infinite. And it's interesting to take periodic groups and so on, as long as they are not too large. Okay. So there exists a lattice because of the assumption. When you have done that, then of course G acts on Vk, L over pi L. And when you vary L, that representation depends in general on the choice of L, but not too much. So let me not too much. There is a theorem of Nesbit and Brouwer. That's not very good. Ah, that's better. Sorry, I used the wrong sign. Okay. So there's a theorem of Nesbit and Brouwer. Nesbit was a student of Brouwer. And Richard Brouwer was professor here for many years, which tells you that this G module, it tells you that the semi-simplification which I will write SS semi-simplification in K of L over pi L is independent of L up to isomorphism. It's independent of L up to isomorphism. What is a semi-simplification? In general, when you have a module, and here we have a very simple situation, a vector space over K, let's say E, vector space over K, an action of something, some algebra, then you can apply Jordan-Holder to that, so that you can write the Jordan-Holder sequence like this. Is E, such that all the quotients are simple modules. Well, simple modules, non-zero module for which there are only two submodules, 0 and the full thing. Okay, you can do that, and then by Jordan-Holder, the collection of the simple modules that you get doesn't depend on that, and so you define the semi-simplification to be the sum of the EI over EI minus 1. It's not completely canonical. You could make it canonical, the semi-simplification, but not functorial. So it would be functorial with respect to isomorphism. Let me tell you how you do that. You would take in E the largest semi-simple submodule. Then you would divide by that. In the quotient, you would again take the semi-simple. And you would keep doing. And this way, there is no choice. But in practice, this has no interest at all, because it doesn't matter. Okay, so we see now the theorem of Nesbit-Brouwer tells you that the VKSS is independent of L, and it's really an easy proof. And it is given in all books. So I will not prove it unless I have enough time at the end, which I doubt. So we leave it as we. So now that I think I have described which side is this, I think I have described all the things which give a meaning to the theorem. Because the theorem will then be, you take this representation, and then you will semi-simplify it, then you construct, that is the theorem, a quadratic form which is invariant. And we will see that one can do that with some nice properties. But to do that, I need to do a little game on the lattices. And since I have not found that game in the literature, it's worth telling it. So I fix a V, like I had before, with this K, little k, R, and so on. And I'm interested in the different lattices, L, M, and so on. What I want to do is to define a kind of mean value Lm. To give you an example of what I want, let's take a very simple case. Let's take V one-dimensional equals K. Let's take L to be just R. And let's take M to be, say, pi to the 9 R. So you see the distance between L and M is 9, so to speak. You can. Then the mean value, well, suppose I put 8 first. Then the mean value would be pi to the 4 R. It is a lattice which sits exactly in the middle. But if I took 9, because for 9 it doesn't work, and so I will have two mean values. I will have the small mean value. Now, small means a high power of pi, so that will be pi 5 R, and M plus of Lm is pi 4 R. So I'm going to do that in general. I'm going to write two lattices which sometimes coincide, which we interpolate. I mean, they are just in the middle. I think I will take a little time to explain to you how one can see those things in terms of the building. The Bruatitz building, which is in fact in that case Goldman Ivaori. But let me just do it brutally. So I start with my two lattices. And I give you a formula for the mean values for the lower and upper mean value. Lower and upper, which I denote by M minus M plus. They are given by strange formulas, which I like. M minus of Lm is the sum n in Z of pi n L intersected with pi minus M and M plus. The sum means the submodule generated by. And the second one, you invert those things. This goes here, and now that goes here. Okay, that's the definition. That's a small exercise to show here that you find exactly what I said. That's and these things have a lot of good properties. Oh, they are perfectly factorial. That is, if I have an f which maps V into itself, and if f maps L inside L and M inside M, then it's clear on the formula that the same is true for the mean values. But the thing is not totally obvious. And that is the main thing for what I want to do. So you have the following. The smaller the inf mean M minus of Lm is contained in the plus. Well, that we expected that, and not very far. That is the main point. Pi times M plus. of Lm. So that we had two lattices which were very far apart, and we have constructed canonically. Canonically is essential because after a while we will have a group acting, and if the group stabilizes Lm, it stabilizes also everything I do. So you have that, and they are very closely related. And they have some amusing properties. I mean, that's m plus or minus pi L pi minus 1 m is the same as m plus or minus Lm. This is totally obvious on the formulae because that just means that you're changing some n in n plus 1 in this. So it's really trivial. Much less trivial is m plus of pi L and m. So you put just one pi. And then if you look, you don't see clearly, but the formula is still nice. Now let me try to remember. It would be smaller. I think it is m minus of Lm. M minus by Lm is pi time m plus of Lm. We have formulae of that type. Now, how do you prove them without any effort? It is strange that, I should also say, that's pretty clear anyway, that L intersect M is contained in M minus. Well, that's trivial. But some of the properties are not obvious. The way to prove them is the following. First, you check them in dimension 1. Check in dimension 1. And they are usually totally obvious because the only lattices are just the pi a something. Really nothing to do. Second, use the following fact that if LMM are lattices, there is a direct sum decomposition of V in pieces of dimension 1 n is the dimension, which is compatible with L and M. That is compatible with L and with M. In the following sense, that L is a direct sum of its intersection with the VI and M also. You prove that by using standard things on when you have two lattices, you can choose basis. I mean, there is a theorem in algebra which tells you you can find the basis of the first one such that the other one has for basis the same elements multiplied by scalars. If you use that, it means that. And that would not be true for 3. And when I will say something on the Bruatix building, it will turn out that it is a general theorem in the Bruatix theory. When you have 2 points in the building, there is an apartment which contains them. And here an apartment is a decomposition in sum of lines, a maximal torus. In fact, I'm choosing maximal torus. Okay, so that is what I wanted. And then maybe I will say a little on Bruatix, Goldman and Vaori. Well, remember in the case where V has dimension 1, in that case, the lattices are just the pi n r, well, is k, the r and r, n in z. So it's natural to write down some line where you will put 1 point for each lattice, for each n, and then you will put something in between just to make it nicer. So then you have a space of dimension 1 with integral, and you view these things as integral points. You might say that's not very satisfying. I should really interpret in a concrete way an intermediate point. You do that in the following way. You look at evaluation on V. That is, you look at a map of V to the real numbers. And you put the axioms of evaluation. I mean, you want that V of lambda x is valuation of lambda plus valuation of x, where that one means the valuation inside the field K. And you want the usual thing, V of x plus y is at least equal to the inf. I hope I have the inequalities right. I think so. Do that. Now, if you take a space which is one-dimensional, in fact, there are not so many things like that. You have to decide what is the valuation of one point, and after that, because of this thing, the others will be adding up integers. And so you can interpret these things as valuations. And then the interesting points corresponding to lattices correspond to the z-valued valuations. And you can do that in higher dimension. And that was what Goldman and Hivaori did. They explained in their paper that they followed the suggestion of Weil. Weil was somebody who was always trying to understand the connection between real numbers and p-adic ones. And for real numbers, people who worked with that, a vector space, they use a symmetric space. In a symmetric space, G over K. And the symmetric space can be interpreted as the set of real quadratic forms on a real vector space. That is the symmetric space. And then here the idea is that, of course, in the ultrametric case, you should replace the quadratic form by evaluation. And so he suggested that to Goldman and Hivaori, and they proved that it works very well. The end result is that the set of lattices becomes the set, so to speak, of z points of a topological space, a quite honest topological space, which is called the building. And you see here, the building is one-dimensional. That's because the dimension of V is 1. So in general, that building will be a union, not disjoint, a union of so-called apartments, which are isomorphic to Rn. Just like we had R. But they're glued together, and the whole thing is a kind of simplicial, not exactly a simplicial complex. It is subdivided in cubes. To explain to you, so these will be vertices, they will be lattices. So let me explain how you make up a cube. You start with one lattice. L, we are in dimension 3 here. So in that lattice, you look at the sublattices of index 1, so to speak. The length of the quotient is 1. And the quotient by pi is 3-dimensional. So you split it in 3 lines. And they give you lattices which are very close to lattice L. The quotient has just length 1. And so that will be the 3 which are directly connected. And then you look at D1, D2. It defines you a sublattice of a greater index, and that will correspond to the 3 others. And then you will have the poor lattice PL, which will be just the opposite. So did I make? I think that would be pi L. Now, why do I draw those things? It's because the idea I had in mind to construct this bizarre mean is the following. You have this building, and what I have are 2 points, 2 integral points, L and M. And I would like to define a mean value. The first thing is that those Rn have a natural affine structure. So it makes sense to speak of the geodesic between L and M. You have to prove that, but it's not difficult. And then, of course, I would like to take the mean value. But the mean value has no reason to be an integral point. It is only a half integral point. And then when I try to approximate to see what it gives me my 2 minimum and maximum. Okay, enough of that. Next thing is I have to, next. Now I have to introduce a quadratic form. So we have V and so on, but we assume that we have a quadratic form, non-degenerate, which I prefer to view as a bilinear form, symmetric bilinear form. Now, when you have that, if L is a lattice, there is a notion of the dual lattice. The dual lattice, as a matter of fact, as the lattice is canonically the dual, but the definition is it is a set of all x in V such that the bilinear form, let's call it B, such that B of xy is in R for every y in L. So that's the duality. And it is reflexive. And we can play the game now, the game of the mean value, but using L and L star. So I'm going to take the lower mean value and the upper mean value. The formulae that I gave to you for those mean values show that duality reverses them, you see, because duality transforms a sum in an intersection and an intersection in a sum. So that, in fact, they are dual of each other. And by what I said before, this one contains pi m plus of L star. So what did I do finally? Finally, starting with any lattice, not at all a lattice which is well behaved or something, any lattice, I make up two other lattices, let's call them A and B, 2 lattices A and B, which are dual of each other. B is A star. A is contained in B, which is A star, which means that the quadratic form takes value in A which are integral, but pi A star. So they are extremely close. I recall that if a lattice A is such that A equals A star, then it is called unimodular. I mean, because the matrix representing the form has invertible determinant. So it's called unimodular. So really the good guy, so to speak. And this one is almost unimodular. By definition, I call that almost unimodular. So now suppose you have a group acting. And suppose it leaves stable at least one lattice. And that was our assumption. Then you apply to that lattice this construction. And then you end up with two lattices with much better properties and which are also G stable, because I have done only canonical constructions. So that was the purpose of this part, to construct such lattices. Next, now we are going to forget the L. We are going to remember only this almost unimodular lattice. Now there is something quite nice about that, which is that we are going to have bilinear forms. I never remember if it is, no, it has to be on both. Yes, it has to be on this quotient and this quotient. Okay, let me try to do it. Bilinear forms depending on B, of course, deduced from B on, well, A star over A and A over pi A star. Now, can I remember the formula for this one? Yes, I say formula for this one is the following. You take two elements x and y in A, and you take B, a binary form with value in little k, of course, with values in little k. We are working now in the residue field, and we want things over the residue field. If you take x and y in A, if you take B of xy, and then you reduce it mod pi, you find something which is in K, because A is in A star. But also, if you modify it by pi A star, that is, if y is in pi A star, that is, y is pi z in A star, what do you find here? You find pi B of x z, and because z is in A star, this is in R, so this is in the ideal pi, so it doesn't count. So you do have the bilinear form here. And it's easy to see it's non-degenerate. And you have a similar formula here, but you have to multiply by pi minus 1 or something. So you get two, you get bilinear forms, non-degenerate, on both A over pi A star on the two pieces. And what is the other one? Other one is A star over A. All right. Now, there is a well-known theorem of Springer, We proved that long ago in the 50s, which tells you how to connect quadratic forms over capital K and little k. It connects quadratic forms on K and on little k. And the best way to state it is to state it in terms of the Witt-ring. Well, some people objected to me that the Witt-ring has a different meaning. So people say the Witt group, but it is a ring. Okay, let me write Witt of K. That is the classes of quadratic forms up to isomorphism and where you consider a hyperbolic form like 1 minus 1, I mean x squared minus y squared, you consider it as 0. So you divide the natural Grothendieck ring of quadratic forms by the hyperbolic ones. Depending on what you do, this is a good thing to do or not. For instance, in my lecture next week, I will spend a lot of time with the lambda operations. The lambda operations are not defined on that. But the difference is really minimal. So what Springer did is to define two maps. Witt of little k. And in the following way, you take a quadratic form over k and you write it as a sum of squares. You write it sum of alpha I xi squared, alpha I in k, multiplicative. Now, since the squares don't matter, you may assume that you have either alpha I invertible, valuation 0, or alpha I equals pi beta I, where valuation beta I equals 0. And now the homomorphisms of Springer are the following. It maps the form, the first one, it maps into the sum over the I. I mean, you have two different types of I. So you, inside the form sum of alpha I mod pi, which is in k, xi square, well, the variable doesn't matter. When people usually write those things like this, alpha 1, alpha, and goes to, by R0, the alpha R reduce mod pi, and you stop when you don't have any more of the first kind, and the R1 is the other one. You map into the beta. And of course, you have to prove that it doesn't depend on the way you wrote your form, but he proves that. You can find that in many books on quadratic forms. For instance, Lam has a very good book which explains that. It's not difficult. And what we have here is that our two forms are the Springer forms, in fact. That is, here, the quadratic form we find, that is the R0. And here it is R1. Now, the way I remember it is that the good case is A equals A star, because that means excellence. Then in that case, everything is good, and so that is R0. R1 is a kind of residue, you see. It is typical of what one does in those things of measuring the badness. Okay, so now we have got slightly better theorem. That is, we have that if we have a group representation which is orthogonal, we have made up two lattices which are like A and A star, which give us two quadratic forms which we really know. Oh, incidentally, when the ring is complete, I didn't use any completion hypothesis, but if the ring is complete, then the theorem of Springer is very nice. It tells you that these two maps given by R0 and R1 give you an additive isomorphism. The multiplicative structure is easy to recover. But that is only when the ring is complete, if R is complete. Okay, now let me try to prove. No, I still need a little piece of information. Okay, what is a little piece of information I need? That as information has nothing to do with R, with it is just something of a field. So the statement is the following. Suppose you have a vector space. I should find a name different from all those. Can somebody suggest a name for a vector space? Come on. Hmm? But with a bit saying, my God. No. Okay, all right. Let's write it C. It doesn't matter. I have a vector space. No, I don't want to write with that stupid joke. So, suppose you have a vector space C with an action of a group G, where here G doesn't have to be finite. And then you take the semi-simplification SS, semi-simplification, which are already defined. And then you suppose that you have a quadratic form, a bilinear form, well, or let's assume characteristic not 2 because I don't need anything. Quadratic form, non-degenerate, so characteristic not 2. But it would work for alternating form also. On C, which is G invariant, and then I want to show, that is the theorem, that there exists one also on CSS. And the proof is a little construction with not much interest, but no, and I want to say a little more. And no, I want also, let's call it Q here, and let's call it Q SS. What I want to add to the theorem is that QSS and Q have the same image in Vit. I did not give a name to the vector space. Well, I'm going to apply it. I think I'm going to apply it to the small one. So, okay, same image in Vit. Okay, or more simply, they're isomorphic. QSS is isomorphic to Q as a quadratic form. That is, you disregard the action of G. Of course, the action of G is not the same because it was not semi-simple, but as quadratic forms, they're the same. And the proof is a little construction. Proof by induction on the dimension. Of C. You may assume, Bourbaki would say, we may assume C non-zero. If not, there is nothing to prove. And we can choose in C a simple submodule. Let S in C be a simple submodule. And we can speak of the orthogonal of S with respect to the bilinear form. So let's call S, I don't know, maybe like this, equals orthogonal. Then there are two cases. The first case is a case where S is contained in its orthogonal. So that means that the quadratic form is well, that means S is, what is the name for that? Isotropic. It's totally isotropic. But then you have those embeddings, and S is a dual of that. And on the quotient here, you have a non-degenerate bilinear form. So on S orthogonal over S, you have the same situation, but with a dimension smaller. And so by recurrence, by induction, you know there is a form of the type I want. On the other hand, I should have written the C semi-simplified. See, because of that, it will be the direct sum of S truc over S, and C over S plus. And those two things are duals of each other. So you can make a quadratic form by taking the duality between those things, and that will give you a hyperbolic quadratic form. So in fact, up to hyperbolic, well, I'm cheating slightly, up to hyperbolic C, I'm reduced to that. And then you win by induction. Okay. Now I think I can probably prove my theorem. So incidentally, it's quite possible that there is a proof in the literature already, that I don't know. But I had more fun constructing a proof and making those constructions. And they give things which are canonical, which is something I like. So let's go back now to the original problem. We had our orthogonal representation. We wanted to reduce it mod pi and prove that on the semi-simplification there is a quadratic form. So what we do is the following. First, we use something which I should have numbered, a theorem I proved. There exists an L lattice with the nice property of my A and B, that is with L contained in L star, in L dual, and L star. And I'm free to choose any lattice I want, because I know already by Nesbit-Brouwer that the result doesn't depend on that. So let us choose, for instance, that lattice. If I take the semi-simplification, L star over pi L star, semi-simplified, that is really what I want. That is my VK. Then it is a sum of L star over L semi-simplified plus L over pi L star semi-simplified. All right, but I have proved that this thing has a quadratic form invariant, and I've also proved that it goes to the semi-simplification. So here I find the quadratic form, and here also, and they are invariant. And so I've proved the theorem, because I get it in two pieces, and also the extra information is that the quadratic form I get on VK as for class in Vit K, the sum of the R0 and R1 of the original quadratic form. Then I finished on time.
Give another proof of Springer's theorem?
Of what?
Does this give a more explicit proof of Springer's theorem? By
no,
giving the lattices?
not really. In fact, in the literature, you find a proof by Lenstra, which is rather close. He does not introduce exactly my mean value, but almost. He does something similar. But the direct proof in LAM is very simple. Really, there is no problem. You see, in LAM, what he uses is that we know by Vit that the quadratic forms are known, essentially, if we know the ones in dimension 1 and the way they relate in dimension 2. They are generated by dimension 1 and related by dimension 2. So when you want to prove maps do not depend on something, the real work is in dimension 2. And
what about characteristic 2?
Characteristic 2, the very serious problems are, but to which experts have no solution, is you have a quadratic form. You reduce in characteristic 2, you get an alternating form, but whether it corresponds to a quadratic form or not, even the table of Atlas, I think they don't give you that. There seems to be no recipe, like in characteristic 0, there is some character sums. But even for algebraic groups, for instance, if you take G2, all the representations of G2 in characteristic 0 are orthogonal, but then you reduce them in characteristic 2, and which ones have an invariant quadratic form? And I think this has been done, but the answer is absolutely not something simple. No. One would like to have something with root systems, of course, to do it, but